Hi viewers, welcome to LMS Solution. Today I am going to see about MATLAB simulation of UPQC for power quality mitigation using an ant colony based basic control technique. Not implement this concept UPQC for power quality mitigation, and also here we are implementing a fuzzy logic control. That fuzzy control going to be tuned by means of ant colony optimization. This is the overall system used for simulation. This system consists of grid system. This is programmable grid used for creating voltage, sag and swell, and it have nonlinear load. That means three-phase rectifier with the RL load with a THD of around 22.24%. So in between source and load, here we are using UPQC. This UPQC consists of shunt active filter and series active filter is connected with the common and distinct capacitor. The shunt active filter is connected to the grid system in parallel, and then series active filter is connected to the system in series manner by using this transformer. We can see the working of this normal UPQC, the PA control UPQC. Already we posted that video. We can check my YouTube channel for more explanation about that concept and then different simulation results. Here we are going to use fuzzy logic control for shunt active filter. That means that filter used for controlling the DC voltage of that shunt active filter and series active filter. Here we are going to use that fuzzy logic system. This is a fuzzy logic. Here we are created the fuzzy logic control. That means here we are implemented Fuzzy-PID controller. This going to act as a fuzzy proportional derivative controller, and then this will be act as an integral controller. Here finally you add here, and also here there are different factors there. One is KE and then KCE and then KU. That means this is tunable parameter of the fuzzy logic proportional derivative controller. That means this is nothing but input scaling factor. This is nothing but output scaling factor of the Fuzzy-PID controller. And then go inside this system. So this is a fuzzy logic system we created inside. This is for input membership function. This input membership function going to be optimized in this system by using ant colony optimization. Here you can see that, but here we are using different kind of tunable parameter for each maximum membership function. So this parameter going to be optimized by means of that ant colony optimization. And also you can see here, right, in order to create rule base. So here also we are using different tunable parameter. This is also going to be optimized in the fuzzy logic system. This is the fuzzy logic system we are created for that voltage control of shunt active filter and the series active filter. And then how we are going to integrate this control logic. Here we are going to measure that THD of the grid current. The THD of the grid current going to consider as one objective function. So another one thing here you can see here, integral of absolute error, integral of time multiplied absolute error, integral of square error at the root mean square error. So these are the one way consider another objective function for optimization. This is going to be integrated with the ant colony optimization to tune the parameter of fuzzy logic system. Next I'm going to open the code for the ant colony optimization. So these are the code for this. Next I'm going to open the cost function. Here you can see here that TE, KC, KUX, ZN here. These are the tunable parameters. So here we are going to tune 6 parameter in the fuzzy logic system. Here you can see that this is a code used for calculating the cost function. Now I'm going to simulate this model. I take my code. You can see the optimization process. Here you can see that the optimization process will be started here. After 10 iterations here we are consider only 10 iteration. So you can consider normally you can consider 100 iteration or 500 iteration. Just we consider only 10 iteration for showing the results. Now the iteration 2 is ongoing. After every iteration we will get some basic cost and then best value for that tunable parameter. So that parameter can be finally we can see in this the display, and also you can see the cost function optimization with respect to iteration also finally. Here that the iteration is now the iteration is not going on. Here you can see the variation of n number and then n parameter. Every iteration you will get some best parameter. After 10th iteration, you will get final insights. We will wait for completion of that optimization. Now you can see the variation of the cost function with respect to change in gradation. After 4th iteration, it's a variation of the cost function like absolute error, square error, root mean square error, integral of time multiplied absolute error, and then TST of the group current. Next, you can see here that after 5th iteration is the final best cost value for 4 more iteration for getting the final optimized results. Normally, this optimization you need to do for a trial of 50 trials or 100 trials. So then only you can find it the best result from the final 50 trials. Try to execute this optimization for 50 trials, and then you can get the best results from the 50 trials. Yeah, and then finally you can use that optimized value for your physiologic system in order to get the better result. Now 8th iteration is ongoing, 9th iteration is ongoing, one more iteration. Now 10th iteration is ongoing. After 10th iteration, we will get the final best result, and then that result will be included in the Simulink model. Finally, we will get the final insights from the Simulink model. 10 iterations almost completed. This is a final optimized value. Here you can see that final result for this optimized value. I'm going to simulate this model again for that mean harmonic voltage sag and swell. We are getting the load voltage getting 1 per unit voltage always. During that time, you can see that this is the injection of the UPQC because of and then mean injection of voltage via series active filter, and also we have to check the result of input current. Here you can see that so input current is in sinusoidal nature, right? And then we need to check the THT of the input current. We need to see the THT around 2.44 percentage. Is less than 5 percentage. So this is the operation of UPQC for power quality mitigation by using on-call optimized logic control. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification for upcoming videos. Thank you.